Save the date, Data Skeptic listeners. May 30th, 4 p.m. Pacific Time. We're going to do Data Skeptic Live. More details at dataskeptic.com/live. Right now, that's going to point you over to a meetup invite. That's the best way to stay up to date. I'll be putting some more stuff on that link, so as the day gets closer on May 30th itself, make sure to check dataskeptic.com/live for more details. This week, I'm joined by Tim Lillicrap to discuss the question posed in his recent paper, What Does It Mean to Understand a Neural Network? I'm going to ask him that and a bunch of other hard questions.
My name's Tim Lillicrap. I have affiliations with DeepMind, which is a part of Google, and as well UCL, University College London.
Could you tell us a little bit about your career and how you got into machine learning and AI and topics like that?
So I guess around when I was an undergraduate, I took a cognitive science course, which I think was really the turning point for me. It got me interested in philosophy of the mind and figuring out how we think in some sense. And then I was in University of Toronto when I was an undergrad and was fortunate enough to take some neural networks courses from Jeff Hinton, who was there as a professor and teaching undergraduate courses. And that got me really hooked on thinking about neural networks and deep neural networks. And from there, I kind of went off and did neuroscience during my PhD and postdoc, but I've kind of slowly come back into machine learning.
Philosophy of the mind doesn't show up on a lot of sort of traditional computer science curricula. How is it that you were able to integrate that and also understand the more mathematical sides of these topics?
Most of the everyday computer science we do is working with data structures and trying to transform numbers and so on. But on the other hand, I would say that even fairly early on, there was some connection to the sort of philosophy of mind kind of ideas. Turing famously proposed the Turing test very early on in the development of computer science theory. And I think so there has been sort of a bridging interest the whole time, in part because, why is that? I guess because we have this question the whole time about what it means to think. And in a certain sense, computer science has sort of understood that as what does it mean to compute? And there's been a bridge built, I guess, at each step along the way as we've gone into that.
Oh, well, depending on how lazy I want to get as an interviewer, the paper that I invited you on to talk about poses a series of questions. So I'll just do it once and start with the title. What does it mean to understand a neural network?
Yeah, that's right. The title is a bit funny. I mean, there's actually probably a bunch of ways to interpret that title. And I should say really from the outset that the paper was aimed maybe most at a neuroscience audience. So it's really, I think, trying to speak to neuroscientists who are in the process of trying to understand the brain, understand biological brains in particular, and how they work and how they compute. It is a paper maybe written from the perspective of where we find ourselves right now in machine learning and deep neural network theory, but then trying to take some of the recent results and ideas and reflect them back into neuroscience.
In terms of these two fields, I'm wondering if you can describe the relationship. I mean, I do bump into some people that kind of share both worlds, but the Venn diagram does not overlap as much as you'd think between machine learning and neuroscience. What are some of maybe the successes or inhibitors that can help or hinder the ways in which these two fields can share information?
Depending on who you talk to, there's either been massive amounts of transfer and it's sort of an easy thing that happens all the time, or, there's almost no crosstalk. And I don't know, I feel like I don't get too bothered about that. And I think it's just sort of a case by case basis where there might be transfer and interesting ideas flowing one to the other. I think sitting in between them is certainly where I've spent a good deal of my time and thought, but there's very successful practitioners who are just totally ignore the other thing that's going on. I guess maybe to connect this question back to the paper, though, there's been this huge sort of recent set of successes in machine learning and in employing deep neural networks to solve all kinds of problems that we couldn't solve before. And I do think that there's at least one particular story that's coming out of that progress, which we should try and take seriously over on the neuroscience side. That's what this paper is kind of about.
So one of the areas that the paper delves into is the notion of intermediate languages. Can you talk a little bit about what those are and why they're necessary in helping to understand a neural network?
Thinking about this from a perspective of neuroscientists, I think for a long time, people doing neuroscience have wanted to, in some sense, understand how the brain is computing. And sometimes the functions that the brains are computing are incredibly complex. They're complex enough that we really do not understand how they're computing what they compute. And so there's a sense in which you'd like to be able to describe that and have a scientific language that we could talk to each other with that lets us say, this is how this bit of brain tissue is computing this complex function. Maybe to ground all of the discussion going forward, I'll pick a very particular one. One I think has almost become common currency now, which is categorizing an object in an image. So this is sort of a canonical example in machine learning. And you can imagine lots of animals do variants of this kind of computation, and certainly humans do tons of this kind of computation all the time. It's very sensible to ask, and people have asked for ages, how are brains performing that kind of a problem? And could we have a language that would let us get a hold on that and describe what's going on as these computations unfold? That, I think, is really the thing that people have had in mind, the aim that people have had in mind. And I think that the recent results that have come out of the deep learning, machine learning community cast a bit of a light on this, a funny light on this, which is that maybe that is not the best question to ask. Certainly, maybe it's not the best kind of question to start asking right now.
Well, what is the best question to be asking right now?
If we look at all the progress that's happened in deep learning, we have this picture where we can now build, say, large networks that compute a function like that quite easily. So in fact, we can specify the learning algorithms and the network architectures in a couple hundred lines of computer code that will train a network to perform that kind of a task quite easily. And we, as human computer science practitioners, can look at that code and pretty much have a good understanding of each line of it, have a good idea how they string together and fold together, and produce the outputs at the end, produce sort of a functional piece of in silico brain tissue. And even though we can do all that, we have almost, I would say, no true understanding of the computations that have been put into those networks after training. Now, I want to distinguish for a moment. What do I mean by true understanding? I think understanding is this sort of very loaded philosophical word that gets us into all sorts of trouble. I just want to distinguish for a moment. I mean, I think for these networks that we train, these deep neural networks that we train now on a computer, we have in some sense a complete understanding of those in that we can look at the parameters, the weights in the network. We can look at how it sort of performs computations on the input, so how it transforms the images from hidden layer to hidden layer, and then finally to the output. So we understand sort of all of the mathematical computations that happen in between in a sort of totally white box way. But when we sort of step back from that, if someone asks you, how does that network know that this image is of a giraffe or this particular image is of an elephant, we have, I think, no good intermediate language that we can sort of talk to other scientists about that let us feel like we really tangibly understand the computations that have been put into that network.
Yeah, we have some tools there. We have I don't know if you're familiar with Lime or SHAP values, or there's kind of a cottage industry of lots of papers of approaches to help with machine learning interpretability, but that's not quite the same thing as the language you're looking for. What's more formal about the language?
So there's a bunch of approaches in the literature that are aimed at doing certain kinds of interpretability for the neural networks we build on computers. I think that's very true. And actually, I think that that is a hopeful direction. So I would say that there is some possibility there when we sort of dig in and do more and more interpretability work. We may end up finding really useful mid-level languages in some sense, whereby we can take a large network that's been trained and do some analyses on it and come out with mid-level objects that give us some feeling of really understanding how that network's doing what it's doing. So I think that's a possibility. But I also want to say that at the moment, the work in interpretability, even for these in silico networks where we have complete access to the parameters and how it computes and so on, even for those, the interpretability work, I think, is just, it truly is in its infancy. So one of the signs of that infancy, I think, is that thus far, it is almost impossible, I think, to find places where interpretability work is being used by neural network practitioners to push the envelope of performance. So if interpretability work was really giving us these kind of powerful mesoscale tools that let us really understand in a tangible way how these networks were working better, then a real check on that would be that, well, we can turn around, gain insight from those, and that insight would let us push performance beyond what we can do at the moment. And at the moment, I would say it's rare, almost to the point of non-existence, to see that at the sort of edge of practitioners' work at the moment.
Well, maybe a simple example could articulate a base case. In the paper, you share what I believe is the optimal strategy for winning tic-tac-toe. How can you summarize an optimal strategy for that game?
The strategy for sort of winning or at least not losing at tic-tac-toe, this looks pretty simple. So you can get by most of the way by doing things like saying, if there's an open corner, take an open corner. If your opponent is about to win, so that is they have two X's in a row, then place an O at the end of that and block them from winning. If you're in a position to win, so you have two O's on the board and you can put a third one, then of course play that and take it. There's a relatively compact set of rules that I can convey to you in natural language English that tell you precisely how to play well in tic-tac-toe. So they really sort of give you a full understanding of the game, even though actually there's something like about 250,000 different possible games of tic-tac-toe. If you look at all the permutations, it's something like on that order. So even though there's something like 250,000, I can give you this very compact description of how to win, or at least how not to lose at tic-tac-toe. And I guess in contrast, when you look at things like identifying images or identifying objects in an image, or playing a game like Go, actually giving a compact description in language, thus far, we just have no idea how to do that. All of our languages, that is like English language plus a bunch of computer science language plus a bunch of math, I think has kind of failed for us as scientists.
So a game like tic-tac-toe, we can elegantly summarize it with a couple of rules. With Go, it's not quite as clear. Obviously, some rules could get us a certain distance, like my life depended on it that I have one day to train a complete novice who's never seen the game before. I'm going to approach that training exercise in a very different way, give them some heuristics that get them as far as possible. How far do these heuristics in games like Go work before they're not even useful or not competitive in the game? Can we get epsilon close to optimal, or is this even a hopeful path?
Yeah, I think it's maybe hard to answer in general, but in a totally general way. But I think Go is a good place to ask that question. And certainly there are things that I can teach you as a novice in one day that would let you beat other novices quite handily. So in Go, I can tell you things like take the corners first, then take the sides, then go after the center territory. And this will give you a huge advantage over someone who doesn't even have that principle. On the other hand, there are published mostly in Chinese, Japanese, Korean, I think on the order of 10,000, maybe more books that are written about the strategy of Go. And the situation is such that even if you read volumes and volumes of books basically discussing the principles of how to play Go well, so even if you read 100 of those books, you will lose easily to a decent pro who has basically just played the game a lot. If the principles put down in those books were worth their salt, you should be able to sort of execute on them and then perform well. But the fact is, actually, there's a lot of principles that even low-level pros have in their heads, which we have not yet been able to sort of distill down into principles that you can write down in a book and convey to another human easily. So then you might ask, well, how did these pros get to that point? How is it that a pro can beat someone who's read 100, 1,000 books? Well, they've basically done a lot of training. So they've seen a lot of data and they have implicit learning mechanisms running in their heads, which are absorbing lots and lots of bits from these games and laying those down into synapses in their head. And they don't have explicit access to that. So what the networks in their heads then tell them about how to play. They can have feelings about what moves they ought to play, and they might even have some post hoc justification for a move they play. We kind of know that those are not very well aligned. If they were well aligned, then they should be able to just write down those principles. That's kind of how we know that.
It almost leads me to wonder if we can know much at all about a neural network if we have to accept that it can't even explain itself in all cases, or perhaps that it's in danger of coming up with some ad hoc response. Do you think there's any time worth exploring this notion of self-explainable systems?
There almost certainly is something interesting about going down the self-explainable route. So, could a network sort of learn to inspect parts of itself and then sort of report on that? I think that's definitely an interesting direction for research, certainly in machine learning. I don't know if it's going to help too much for neuroscientists in the next little while. And maybe this is what I should try and come back to. As humans, we certainly have a certain amount of conscious access to parts of our own networks. And we can report on those. But then as well, we have lots and lots of intuitions, which we don't have conscious or explicit access to, at least in the sense that we can sort of verbalize those in discrete English language or even discrete computer science language. While I think that's probably a really interesting direction of research for machine learning, it's not clear that this network's trying to explain parts of their own workings is going to help for neuroscience in the next little while.
Thanks to this week's sponsor, Terminus DB. Terminus DB is an open-source, full-featured, in-memory, graph-driven database management system with a rich query language. That's a lot of goodness. Open source, don't have to sell you there. Full-featured, does everything you want in memory, so it's fast. Graph database, connects graphs. One of the more difficult to work with structures of data. If you've got a graph problem, you need a solution like this. And Terminus DB, as they say, is a database management system. You can spin up the server and you're off to the races. Now is the time to explore it for yourself and see if it's right for the problems you work on. You have a little extra time as you're stuck at home during the pandemic? We'll get to know the Terminus DB community. There's a lot of support available for this open source product. And it does a lot more than I could have told you about in this ad. For example, I didn't even get into how Terminus DB adopts a delta encoding approach. That allows it to do data updates the way Git does source code updates. When you need to manage your data very carefully and know its provenance, know how, when, and why it changed. Terminus DB is a tool you should check out. It's collaborative features like that make this an ideal solution for building data sets as well. If you're lower on the stack, DevOps, data engineers, people like that, you guys head over to terminusdb.com. Everything you need to know to set this up is there. People higher in the stack, data scientists and ML engineers, you guys go check it out as well. If this provides the features you need, tell your coworkers you want it in the stack. Either way, it's a neat piece of technology to check out as you build your personal repertoire and toolbox. terminusdb.com.
Well, I'm a Go novice, I'll confess. A moment ago, you gave me my first bit of wisdom, take the corners first, I think it was. And if I went out there and started playing with it, I guess I would grow to trust it because I would start to win or see the advantages of that. And I would kind of maybe over time learn to appreciate the wisdom you gave me. But I wouldn't off the bat know why that's the right thing unless you said, oh, there's this theorem that proves it. And maybe I could understand the theorem. But I start from this sort of like, I'll just follow my marching orders and I'll learn over time. Whereas I feel like a machine learning approach, take something like AlphaGo, it's going to do this deep search, pruning, and all this kind of stuff. And even if it comes up with the same heuristic in some abstract way, it's done the full derivation or explored every search tree, whereas you kind of did that for me when you taught me that rule. Does this mean that maybe at the current time machine learning is just this exotic different form of learning, or are we closer than I'm thinking to the human way of learning?
Just a couple things to unpack. In the first work on AlphaGo, actually, it did get all the sort of heuristic conveyance, heuristics, because when that was trained, it was initially trained using a lot of example human games. So in some sense, we kind of downloaded to it the sort of high-level gist of what kind of moves to explore playing with first. That was actually in the original paper. In the subsequent papers, though, the human data as far as sort of what kinds of move to play were removed, and it had to discover those kinds of things, those principles for itself. It should be said, the discovery of those principles cannot be boiled down to theorems. They're not sort of provably the case. In the end, I would say it is kind of closer to what's gone on with humans, at least in some sort of historic sense. So in effect, it's trying things on the board, it's seeing ultimately how they work, and then backing up the value of those wins or losses into what it thinks about the value of board states, and then ultimately into the weights of its network. And I think that whole process actually is very much like what humans are doing in this case.
And the learning process, as the paper points out, compressibility is a fine way to describe it. That, out of an image, which is really just a very, very large, n-dimensional number. If it's a small image of 200 by 200 pixels, that's still a really huge number. It's a mapping from this large space of numbers to typically some finite set of classes. And that's a function, and that function could be massive or really tiny. The tiny ones seem to be the useful ones, and also the ones that do capture the system, I guess, in some way. Is there anything formal we can say about compression? Can we compress too far or not enough? Are these formal concepts that can be studied very well at this point in time?
I think there's an awful lot that can be said about compression in a general sense in computer science. What we can say, I think, about compression for, say, these kinds of networks that do recognition of objects in natural images or that play Go, I think there's very little at this point that we can say very concretely and formally. Most of what we know is through empirical experiments, these kinds of networks, and I would say it's pretty early days. That's the general picture. To make this question a little more concrete and bring it back to sort of the neuroscience case, You can imagine doing something like this. If we really had really fantastic compressibility algorithms, then we might think we could do something like this, which is we could train a big deep neural network to classify images. And we know that at the moment, we don't really, in some sense, understand what's going on in all those weights. So there's like millions or tens of millions or hundreds of millions of weights that make up the parameters of this network. It computes as outputs, and all of that's a bit mysterious to us. But we could imagine saying, well, if we had a fantastic compression algorithm, then maybe what we could do is we could take that gigantic function approximator, we could push it through this compression algorithm, and ideally what we'd get out the other side is a compact and human understandable, say, piece of computer code that someone could read and inspect and say, hey, like now I really understand how this network is performing the operation it performs. The reality is sort of twofold. The reality is that we certainly do not have compression algorithms that would give us that. So I think we're a long ways off that. On the other hand, people have spent a bunch of time trying to compress some of these very large networks into smaller networks at least, and sort of asking the question, how small a network can I build that would still perform very well? So that would still have, say, 99% of the performance of one of these very large networks that we don't understand. I guess the answer there is sort of, there's a couple of things to say about it. People have managed to crunch networks down much smaller, but those small networks at the end of the day are still pretty large, like on the order of, for say, something like image recognition, maybe more than a megabyte of data. And that data is still not really penetrable to a human. I mean, effectively, these are sort of still weights in a neural network that don't mean all that much to us.
I guess we understand it as human beings at the arithmetic level or at the tensor level. We can follow the calculations through. So where is it that we end up losing it? How did we start this machine, ask it to do something, we know all of its pieces and how they work, yet we can't totally explain it?
That's really part of the question, and I think also leads us towards the answer that we sort of talk about in the paper, which is that, look, we understand the neural networks in silico in a totally white box sense. We understand how the matrices operate, how the nonlinearities operate, but we don't understand what it does at the end of the day, at least in sort of like this colloquial sense of the meaning understand. And so how did it get there? Actually, it got there by applying a small set of very relatively straightforward learning rules to a lot of fairly complicated data. That's usually the combination. One of the things that's kind of magical about the current situation is, even though these big deep networks are pretty mysterious to us, we're building them all the time, and we're doing great engineering with them all the time now. And we do that pretty easily, and we communicate about how to do that to each other as scientists in papers that are 8 pages long most of the time. Right? So there is a way to do that. It's just that the content of those papers is almost entirely focused on objects other than the innards of those networks. So they say almost nothing about the innards of those networks most of the time. I guess we kind of distill it into sort of 3 things, although there's kind of different ways you could cut this up. But in effect, most of the papers we work with focus on describing the architectures of those networks, describing the learning rules that are sort of used to alter the parameters in those networks, and the loss functions that are optimized by those learning rules. These are kind of the fundamental objects that we work with, that we employ, that we think about a lot. And those are quite describable in the math that we have, in the code that we have. And we're making great headway by thinking about those kinds of objects.
So everything we do in the artificial sense in machine learning is running on a computer, so we can model that as a generalized Turing machine. Is there any reason we have to think that that's a limit, that the brain could be taking advantage of some, I don't know, I've heard everything from quantum or relativistic effects or who knows what, but some sort of gotcha where ML's never going to, quote, achieve a human level because it's missing a piece of hardware somehow?
So there are lots of big gulfs in our knowledge and mysteries that remain as far as, how our brain's doing what they're doing and how do they solve the problems they're solving. But actually, I think this is one of these cool cases where in the span of time from, when I was in undergrad to now beginning to work as a scientist in the field, we've basically got an answer to that question. Now, I'm sure you will find people who disagree, but I think we've got a fair bit of certainty now. Almost everything isn't really sort of some magic there that brains are taking advantage of. I think if you can run large enough matrix computations on your computers as is on floating point numbers, I think the evidence is coming in now pretty steadily that you can probably do anything that a brain can do. There's some funniness around things like some of the problems that we solve as creatures who have fantastic motor control. We have these great sensory apparatuses, like we still don't have artificial skin that's nearly as good as in robotics as humans and animals have. But in terms of the actual sort of computing, I think the evidence is rolling in that it's enough and that you don't need necessarily sort of funny quantum effects, or you don't need like funny effects from the spiking networks that run in brains. That effectively large matrix operation using floating point numbers is probably enough. And I think we know this from all over the place. We know this from looking at object recognition stuff, which is just getting better and better all the time, and all the way to the other side of things like playing Go, where it's about sort of the deepest kind of reasoning that you might engage in. And we see networks just basically working every time we can bring them to bear on a problem like these.
Yeah, there's quite a burden of proof in saying it's something non-Turing complete, I suppose.
That's exactly right. Like if you've already gone all the way from sort of these very perceptual tasks, pattern recognition tasks, all the way to kind of these sort of deep kind of reasoning tasks, we see these in silico networks functioning very well. There's a big burden of proof on someone who says the brain really has something sort of fundamentally computationally special that it's bringing to bear.
What are some of the things that are coming out of the neural networks world that you think are going to be, or maybe presently are already becoming, the most impactful in terms of their ability to translate into neurology?
So one thing that's happening, and is kind of a no-brainer one, is that, neuroscience, like many other fields, is experiencing a bit of a big data revolution. So now people are dropping electrodes in and recording the sort of situations where you can record, say, 10,000 neurons at once, or you can set up 2-photon microscopy where you record 1,000 neurons at once, or even full brains. And obviously, there's an extent to which, when you have that volume of data and you ask human practitioners to sort of look at it and understand it, basically there's just a real limit to that, what people can sort of grok in terms of data sets at large. So, one of the obvious ways that AI will play a part is just in being able to develop tools that will let humans, neuroscientists, look across massive amounts of data and get some kind of understanding about it. At the same time, and this is maybe really part of the aim of the paper, I think that there's a couple things you could imagine trying to do with those large amounts of data that are beginning to roll in neuroscience. One of the things you could do is the sort of what I would say is maybe the slightly more traditional thing, which is you look at, say, a bunch of neural activity and you try and deduce from that how a piece of tissue is computing whatever it's trying to compute. And I should say, I want to make very clear, in some cases, in some simple cases especially, I think that's a very worthy endeavor and probably will work well. But on the other hand, I think in a whole bunch of cases, especially where animals or people, brains under study are performing complex functions, the project of going in and looking at a bunch of activities during some task and then trying to deduce how is this piece of tissue computing what it computes is probably a bad way to spend your time. In a sense, you could try and go and do this for a piece of in silico tissue. And actually, the stage that we're at with the mathematics of interpretability and understanding what's going on in these big networks, that's not going to buy you much, right? The other thing that maybe we're getting out of this revolution in deep learning and machine learning is that it has, I think, provided some clarity that maybe what we should be turning our eyes to explaining are these fundamental pieces, architectures, learning rules, and loss functions, which are really the objects, the language in which we really are able to convey to other scientists how do these things work, in a sense. It's funny because having given those, you still maybe don't have the whole picture because, of course, it's really the interaction of those things with data that gives you kind of the full network that does what it does at the end of the day. But I guess, nevertheless, I think focusing on studying those aspects of brains will be much more productive, at least at this point.
Do you think we're going to observe that the substrate is doing calculations in sort of way we're expecting? Or are we going to be able to find a configure of neurons and saying, hey, look, it's doing a fast Fourier transformation? Will it be that transparent at some point?
I think in some pieces of tissue, especially where that piece of tissue is very specialized, And here I'm thinking about, there's been some very cool work about how flies do navigation. And it actually turns out that they have this kind of ring of neurons in their head that are part of the sort of orientation navigation system. So I think in some pieces of tissue, especially where the sort of function of that piece of tissue is clear enough, we, the sort of neuroscientists collectively, will really be able to sort of zero in on that and truly understand, yeah, this piece of tissue is doing something, for example, like a Fourier transform. And that is, I think, super cool, and we should do it where we can. On the other hand, this is maybe the but part. A lot of the things that brains are computing are sort of actually quite complex and are learned from digesting lots of data. So really, the brain doesn't have much of an answer to it. There are millions or hundreds of millions of synapses which are relatively untuned at birth. And the setting of those synapses as a result of interaction of learning rules with the data that's experienced by an animal. I think that then if you're going in looking for something like an analog of Fourier transform in some piece of tissue, in that case, it's first of all likely to be much harder. And second of all, it's actually less clear that it will be truly useful, both in terms of understanding that you can convey to other computer scientists, and probably even in terms of kinds of medical interventions or something that you might want to bring to bear.
So this is a great paper. We'll have it in the show notes, of course, and I encourage people to use it for one thing as like a trailhead. I know there's some, as all papers have, of course, references, but this is really the culmination of a lot of thinking in different areas that you've synthesized. Would you mind just sharing some broad strokes about some of the inspiration for the work?
A lot of this thinking is a distillation of conversations that I've had with Conrad Cording, who's the other author on the paper, as well with Blake Richards, who's a collaborator who is really sort of much more deep in neuroscience than I am now. And so it's really this sort of result of like reflecting over the last 5 or 6 years and talking to many people, but in particular, these two guys.
And tell me a little bit about what's next. You can talk about maybe what you're working on personally, or at least broad strokes methodologically. What's got you most excited in your day-to-day?
At the moment, I spend most of my time doing machine learning work. I am interested in continuing to think about this intersection of machine learning with neuroscience. There's kind of two questions I'm thinking about and exploring a bit. So one of them is, I've said now that I think some of the most productive questions in neuroscience could be to go after understanding learning rules and loss functions in brains. And so one question then is, if you want to do that, how do you go and collect data in a neural circuit that would let you make inferences about what are the learning rules that are being run by the circuit? What are the loss functions that it's optimizing to produce the behaviors that it produces? So trying to understand how to do that actually in tissue is really of interest to me. The other half of this is we know that the brain has a bunch of constraints about how neurons are connected, and which mean that there are certain learning algorithms we can run on a computer, but that we know cannot be run given the constraints that we know about in the brain. The other direction that I'm interested in is, can we develop powerful learning algorithms that respect those kinds of constraints? Because looking at that class of learning algorithms may give us insight about the kinds of algorithms that brains might be running.
Yeah, those are very exciting questions. I'm eager to hear some of the answers as well as things progress. Well, Timothy, this has been great. Could you share a little bit about where people could follow your work online?
I think arXiv is usually a good bet. Checking out Google Scholar and arXiv are probably the safest bets. Occasionally, we also have some material that shows up on the DeepMind blog.
Very cool. I'll have links to all the above in the show notes for people to follow up on. Well, thanks again for taking the time to come on the show and share all your expertise.
Yeah, thank you.
Can't get enough of Data Skeptic? Well, you're in luck. We have a brand new podcast with Kyle from Data Skeptic called Data Skeptic Journal Club. Hi, I'm George. I'm a data science student from London.
Hi, I'm Lan. I'm a neuroscientist turned data scientist working in a biotech startup in Oregon. Journal Club is a panel show where myself, George, and Kyle all come together to discuss various news articles, academic papers, and journal articles every Wednesday.
This week, I spoke about a diagnostic blood test that can detect 50 different types of cancer. By analysing the methylation of circulating free DNA, this technique boasts a 90% accuracy in determining the tissue of origin.
This week, I led a discussion about how robots and robotic researchers can do to help in the fight for COVID-19.
We would love for you to join us every Wednesday on Data Skeptic Journal Club for our discussion.
Thanks for listening to Data Skeptic Interpretability. Our guest this week was Tim Lillicrap. Our theme song is Number 5 by Big D and the Kids Table. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. I've been your host, Kyle Polich. Stay in and stay safe, everybody.